This is problem 619, Smith Van Ness, 8th edition. We have a two-phase system of liquid water and water vapor in equilibrium at 8,000 kilopascals. Consists of equal volumes of liquid and vapor. We're told the total volume is 0.15 cubic meters. What is the total enthalpy and the total entropy of our system? So we've got our beginning information here. We've got the total volume, V sub t, is going to be 0.15 meters cubed. Our pressure is 8,000 kilopascals. And what we need to realize is this is, of course, a two-phase system where the liquid and the vapor water are in equilibrium. And so what we need to work with is we need to, if we need to find the total enthalpy and total entropy, what we're going to have to do is we're going to have to figure out the mass fraction or the mole fraction if you want to work in moles, but we're using steam tables, so we'll use mass fraction of the vapor phase is. And of course, once you know that, you know the mass fraction of the liquid phase. So that's what we need to do. So we'll use the steam tables for this, of course. And like I said, the steam tables use a mass basis. And like I said, we'll need to find the mass and mass fraction so that we can calculate the total enthalpy and total entropy. Now, we're dealing with the liquid and vapor in equilibrium, so we got saturation conditions. And earlier I worked this problem through using the saturated steam tables, but what we found is that we had to do lots of interpolation. One of the things you should realize is that probably for this problem, since our pressure is a nice even number and the superheated steam tables are indexed by pressure, we might be able to get by doing this problem with a lot less interpolation. So let's look at the superheated steam tables and look for 8,000 kilopascals. And what you'll find is that on page 717, you'll see the entry for the 8,000 kilopascals. And what we're going to be doing, we're given the information for volume, total volume. What we're going to need to find is we're going to need to find the specific volumes. And so I'm just going to write down the specific volumes right here. We'll come back to them. All right. But now I want to talk about how we're actually going to solve this problem. So like I said, we need to find the mass fraction of the liquid and the vapor. We know the total volume of our tank. We know the volume of the liquid and the vapor phases. What we need to realize, though, is that these molar or specific volumes that are given here, they're equal to 1 over the density. So the volume, or I should say specific volume, is equal to 1 over the density. And where density is the mass divided by the total volume. Density, of course, is equal to the mass divided by the volume. So what we want the mass of the liquid, we want the mass of the vapor. And so what you should think about is if we want the mass, then we need to know the volume of that phase. So in this case, this is going to be either the volume of the liquid. So let's focus first on the liquid. We want to find the mass of the liquid in the tank. Well, we know the total volume of the liquid, right? The total volume of the liquid is going to be half the volume, right? And then do we know the density? Well, yes, we do know the density because we're given the specific volume of the liquid, which is 1 over the density. So that's what we're going to do for both the vapor and the liquid phases. And so I've got this written down here. We have the total volume, and this is just saying that the volume of the liquid is going to be 0.075 cubic meters, and the volume of the vapor is also going to be 0.075 cubic meters. And so putting in equation form what I just said a few seconds ago. For the gas phase, the density, and I'm using gas and vapor interchangeably. For the gas or vapor phase, the density is equal to 1 over V, 1 over the specific volume, and so that's what this term is right here, which is equal to the mass in the gas phase divided by the total volume of the gas phase. And it looks like I'm mixing up my gas and vapor, but you can bear with me. So this is known, and so all we have to do is solve for the mass of the gas phase. Do the same thing for the liquid. Density of the liquid is equal to the mass of the liquid divided by the volume of the liquid. Well, that's just equal to 1 over the specific volume of the liquid. And so we have that right here. So again, what we can do now is we can solve immediately. We can solve these equations for the mass of gaseous water and the mass of liquid water. So I'm just going to bring all these calculations over. Take this equation, solve for M gas, we get 3.188 kilograms of water are going to be in the vapor phase or gas phase. Solve this for the mass of the liquid water, that's going to be 54.19 kilograms. So the vast majority, even though the volume fractions are the same, the mass fractions are much different. Much more mass in the liquid phase. So we just go back to Chem E 202, elementary stuff. We sum up the total mass, 57 kilograms, and then we get the mass fraction in the vapor phase, and you can see that's only about 5%, 5.5%. So now that we know the quality, we can calculate the total enthalpy and entropy for our steam, or for the water in the tank. And so what we need to look up those values. So I've got these tabulated here. The liquid enthalpy is 1317, vapor 2759.9, entropy, liquid and vapor. And then we just plug in our equations in chapter 6, equation 696. Notice we can either have this, your book actually asks for the total amount. So if we just take the mass and multiply it by the specific enthalpy, we'll get the total enthalpy in joules. Or if you have it in the mole fraction format, you will have it as joules per kilogram per mass amount. And if I were grading this, I would accept either one of these answers. Those are fine. And then we do the same thing for the entropy. Have the total mass of the liquid times S liquid plus total mass of the gas times S for the gas, and we get 192 kilojoules per Kelvin. We do it in mole fraction, we get it on a per mass basis. So that's this problem. A lot of it is just getting you to use the steam tables, getting you used to using the steam tables, and then the real key to solving the problem is realizing that the specific volumes that you're looking up in the steam tables are the inverse of the density. And so they give you enough information by giving you the total volume of the tank and the volume of the liquid in the vapor phases, to where you can use this density specific volume relations to calculate the mass, and then from there to get the mass fractions. And then this is pretty much plug and chug here to get the final answers.